Welcome to The Explainer. Today, we're kicking off a pretty amazing journey. We're going to build the brain of an 8-bit computer right from scratch. And you know, every great project, every great adventure, it always starts with one thing, the blueprint.
So, building a computer's brain. It sounds like something reserved for a massive tech company, right? You're probably picturing these huge, sterile labs. But what if I told you that it's actually an incredibly cool and totally achievable project? You know, all over the world, people are doing just that. They're pulling back the curtain, demystifying how computers actually work. They're getting hands-on to understand the magic inside the machine. And today, we're going to see exactly how they do it. We're going to start by looking at the master blueprint for our own 8-bit processor.
Okay, so where do we even begin? Well, we start with the master plan. And for our CPU, this isn't some crazy futuristic diagram. It's actually a beautifully simple concept from way back in the 1940s that, get this, still powers most of the computers we use every single day. It's called the von Neumann architecture. So what is it? Well, the whole idea behind the von Neumann architecture is really about one thing: keeping it simple. Think of it like a recipe book. You've got your instructions, the how-to, and you've got your ingredients. In this design, they both live in the same place. There's no separate pantry for ingredients and library for recipes. Nope, it's all in one shared space. And that's the absolute genius of it. See, because everything is in one place, the processor doesn't need two different systems to get information. It uses the exact same mechanism, the same road if you will, to fetch a command as it does to grab a piece of data. It's this beautiful efficiency that makes the whole system tick.
Okay, so let's zoom in on our blueprint a little bit. Inside this processor, you can think of there being two main characters, a real dynamic duo. We've got the doer, who's doing all the heavy lifting, and we've got the director, who's calling all the shots.
So first up is our doer. This is the Arithmetic Logic Unit, or ALU for short. Just think of it as the CPU's calculator. Anytime the computer needs to do any math, add, subtract, compare two numbers, the ALU is the one doing the work. It's the mathematical muscle of the whole operation.
And this diagram here shows the idea perfectly. You've got two things going in. Let's call them A and B. They flow into this adder, and poof, a result comes out the other side. Our ALU is just a souped-up version of this that can do a whole lot more than just adding.
Now, here's a cool little peek behind the curtain. How do engineers actually design these things today? Well, they don't sit there drawing every single wire. They use a special language to describe what the component should do. You don't need to read the code here. Just know that this text is basically a recipe that a machine can follow to build the actual physical circuit.
So if the ALU is the calculator, who's pressing the buttons? Well, that would be our director, the control unit. This thing is the boss. It reads the program, one instruction at a time, and acts like an orchestra conductor, sending out these perfectly timed signals to tell every other part of the CPU exactly what to do and when to do it.
So let's just put that side by side. The ALU, that's the muscle, the doer, crunching all the numbers. The control unit, that's the brain, the director, reading the script and telling the muscle what to flex. You absolutely need both.
All right, so we've got our doer and our director, but how do they talk to each other? And, where does all this information actually live? Well, that brings us to the next part of our blueprint, the information highway.
Okay, there are three key parts to this whole system. First, you've got RAM. Think of RAM as the computer's main library, where all the programs and data are stored. Then you have registers. These are like tiny, super fast sticky notes right on the CPU's desk for jotting things down quickly. And connecting everything? That's the bus, the main road that all the information travels on.
And right here, this is that von Neumann principle in action. See? There's just one main road, the bus. It doesn't matter if it's an instruction coming from the library or data for that instruction or the final answer from our calculator, it all travels on the exact same highway. One road connecting the entire city.
So, we've seen all the individual pieces of the puzzle now. We've seen the doer, the director, the highway. So, let's put it all together. How does this idea, this blueprint, go from a drawing on a screen to a real working circuit?
Hey, remember that code we looked at earlier? Well, it's not just a description. It's actually a set of instructions for a process called synthesis. And what synthesis does is it takes our design and automatically translates it into a physical circuit that gets etched right onto a tiny piece of silicon. It's like 3D printing, but for computer chips. And this is the dance of the CPU. It's this constant, beautiful cycle.
There's a special little thing called the program counter that always points to the next instruction. The control unit grabs that instruction, figures out what it means, and then tells everyone else what to do. And this cycle just repeats over and over and over, millions, sometimes billions of times every single second.
So after all that, after designing this entire computer brain, how much space do you think it takes up on a modern chip? Take a look at this number. 0.2%. That's it. Our entire 8-bit CPU uses less than 1/4% of the available logic on a modern chip. Isn't that wild?
This just puts into perspective how unbelievably powerful modern tech is. I mean, we've designed a complete functioning computer brain, a machine that would have literally filled a room just a few decades ago, and it fits into a tiny, almost invisible corner of a modern chip. It's just staggering.
So, okay, the blueprint is done. All the parts are in place, but, a blueprint isn't a building. How does this static design come to life and actually think? How does it run a program one step at a time? Well, that's the big question, and we're going to answer it next time when we dive into the absolute beating heart of every computer, the fetch, decode, execute cycle. See you then.